cloud computing brings some of the edge devices for faster computation. So it needs a compressed quantum neural network with basically helps in these quantum enabled chips. And there is also the quantum chemistry applications, which needs quantum neural network compression, helps fit the models to the hardware. And then there is the applications for bioinformatics, which needs compact quantum neural network compression and to extract features efficiently. Also, the financial modeling, quantum models for the portfolio optimization needs faster, more memory efficient. And as we're going to see in the results today, and there's also the defense application, which also needs quantum machine learning signal processing for the autonomous devices, and so to the compression neural network compression reduces the inference time. So in 2024, Liu and Chen from National Taiwan University and from Imperial College London came up with a nice architecture that does both compression and classification. And they got really good compression, which is they reduced from, let's say, original circuit 28,000, 285,226 to down to 10,000 parameters. That's also, but they got their classification accuracy up to 60%. So that is how they did that is pretty interesting. They had two input quantum neural networks. Tensor network multiplies them, and matrix multiplication product state basically gives the weights to the CNN classification, and the CNN classification does the basically the cross entropy loss calculation to do the accuracy performance measure. Okay, so that is basically two distributed quantum neural networks processed, and their output is combined with the tensor product, which is a compression step, and the output is feeds to matrix product state, which is another compression structure. And then the MPS generates the weights, gives it to the classical neural network for classification. Classification CNN does the cross entropy calculation, and then we have the classification accuracy performance measures and all this. Okay, so 2QNN, tensor product, MPS with the classification, and then the classification basically performance measure. So the point is, we did something very similar to this architecture with our sort of like ANSAT circuit, variational circuit, and we compared it to the classical compression circuit with no quantum gates. The first model. Second model, quantum MPS, matrix product state, which is a compression circuit. And the third model is the quantum neural network, which was just with the classifier. And the fourth model is a quantum variational compression circuit with the tuning parameter. And we also did the two input QNN, repeated the circuit with our variational parameters. All right, so it has two quantum neural networks. All right, so now for the quantum circuit models that have the quantum gates, it all has the 4 qubits as an input. The circuit, as we're going to see in the next pages, has CNOT gates, 3 CNOT gates. Now it doubles for the two input model over here, and rotational 10 rotational gates also doubles for the two input model. The total is 13 and 26, and basically the rotational gates basically are parameterized, encodes the input to the quantum gates, and then does the tuning for the learning. And for the control not gate is basically it does the entanglement. So that is for the gates in the circuit. So now the shared quantum circuit that we have is a little bit different from the circuit that in the paper. It has variational quantum circuits, basically gates that are the rotational gates and the CNOT gates. And this is the common variational compression circuit that is in all the models. And so, yes, basically, we compared it to the classical circuit, which doesn't have a quantum gate. We have the MPS compressed quantum QNN classifier model. It has quantum gates, the quantum variational compressor, and the two input QNN over here. All right, so now, yes, basically the first one doesn't have quantum gates. The other four models have its hybrid with quantum gates and classification. Now, the first model doesn't have a quantum gate. It's the classical one. It input convolution neural network. Basically, it has the other layers and then the output. The second model is the matrix product state. It is basically a compression structure. It has quantum gates, and it has the quantum layer over here with the 4 input qubits. And the quantum QNN with the classifier also has quantum gates. This is basically the summary of the layers for the model. And then there's also the quantum variational compressor. This has the variational parameter tuning. And the fifth one is the two input quantum neural network. Two input QNN goes into multiplication. MPS gives the classification weights to the CNN, and then there's the classification. So we did this implementation and compared it to the other models over there. We have the two QNN inputs, tensor product, MPS, goes to the CNN, and then does the classification. Now, the metrics that we did the performance is the training accuracy, the accuracy graphs, performance tables, the memory for each model, the megabits, the parameter count, the inference time, the quantum gate count, and the expressibility, and the quantum gate circuit visualization. So the 5 models basically other than the classical one, has the common variational compressor circuit to tune the parameters, and then it goes through the QNN integration. The performance metrics basically have the accuracy, parameter count, memory size, inference time, and expressibility. And we have the final data results in the next pages. Circuit visualization. Now, because it's classification, we needed a data set that has images, and we don't want to use the full data set, minced data set. So we went with the fashion data set, is less data set, and we had to reduce that as well. We have the training loops for 20 epochs, inference time, expressibility data as well. So the images basically from the fashion minced data set. And we had to reduce it in the code a little bit, so to speed up the training time. And basically, we have the 83% training data and 16% testing data. Usually, it is 80-20. So basically, and this is the training loops for each of the model, 20 epochs, and happily, we got good accuracy results, and it happens that the two input quantum neural network architecture that was proposed in the paper basically got the best accuracy, 0.99. And this is the graphs for, as you can see, the two input QNN architecture got the best accuracy. And this is the data. Basically, The 2 QNN is at the bottom. It has the second column is the memory size. It has 0.02, which is reasonable. It's not the least one, similar compared to the other quantum circuit, and it's not the highest. Also, in terms of the parameter count, basically compared to the classical one, it reduced it from 100,000 to 6,000. It's not the most optimized. The other quantum circuits has the 3,000. Reasonable inference time. Accuracy is the best accuracy, 0.99. Expressibility, as we're going to see in the next page, and this is the expressibility over here. Now, too less expressibility basically cannot learn complex pattern under. Too high, basically, it cannot be, it's untrained. So a good range, it's within the good range which of 0.01. And that is, we can see the first row is the 2-input architecture, and it has the column before the last column. It has expressibility 0.01, which is in between, in a good range. The data for the other quantum circuit models has the least parameter count, and yes, so it's not optimized, but anyways, the point is the 2-input QNN architecture with the compression circuit, tensor product, and MPS generates reasonable reduced parameter count, and the parameter compression ratio is in between the best and compared to the classical. So it has a compression ratio of 15.8 compared. Now the other quantum circuits, because it has sort of like one input QNN, it has better compression ratio, 31. The 2-input QNN has 15, which is reasonably good. Again, the memory size, it's reasonably okay, 19 megabits. Now, this is the compression ratio. Again, the 2-input QNN has a reasonable compression ratio, but the other quantum gates models basically got a little bit better compression ratio. Okay, and compared to the classical no quantum. So that is basically it. This is the code, part of the code. This is the data set over here. We have the quantum circuit, and basically these are the models for the quantum circuits over here. And other papers that we went through over here, these are the reference papers over here. And yeah, so reference papers for quantum neural network compression in a lot of applications. And yeah, so that is basically it. Thank you very much. I would want to thank Dr. Leah, because without Dr. Leah, we couldn't get to this point. And yes, so thank you very much. Dr. Leah, thank you very much.